Hello, I'm Essay, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The turn of the 20th century found mathematics in a state of profound, if quiet, crisis. The elegant edifice, 19th century, analysis, built upon the foundations of Cauchy and Weierstrass, appeared remarkably robust, yet lurking within its wall structures were entities that defied its most fundamental tools. These were the so-called pathological functions, creations of pure logic, that seemed to mock geometric intuition. The most famous of these spectres was the Dirichlet function, a construct that assumes a value of 1 for all rational inputs and 0 for all irrational ones. To the framework established by Bernhard Riemann, this function was an enigma, an object without a defined area beneath it. The Riemann integral, which operated by slicing the domain of a function, the horizontal axis, into ever finer vertical rectangles, collapsed in the face of such dense, wild discontinuity. The gap between what could be conceived and what could be measured had become a chasm, demanding a new, more powerful conception of the integral itself. Into this intellectual breach stepped Henri Lebesgue, armed with a perspective of stunning originality. His 1904 thesis, titled Intégrales, Longueur, Aire, more than merely refine the existing calculus, it rebuilt it from the ground up. Lebesgue had absorbed the pioneering work of his immediate predecessors. He saw in the efforts of Émile Borel the nascent idea of a more general theory of a set's size, or measure, one that could handle sets far more complex than simple intervals. He also recognized in the work of René Louis Baire a systematic attempt to classify the very functions that were causing such trouble. Lebesgue's genius was to synthesize these threads into a revolutionary approach. He proposed abandoning the century-old practice of partitioning the function's domain. Instead, he would partition the range, the vertical axis. The fundamental question changed from what happens on this small interval of inputs to for this small interval of outputs, which set of inputs produces them. This conceptual pivot required the invention of two powerful new pieces of mathematical machinery, both detailed with meticulous care in his thesis. The first was the Lebesgue measure. It is a function that assigns a non-negative value, its length, to a vast collection of subsets on the real line. Its defining property, and its critical advance over the older Jordan measure, is countable additivity. This means the measure of a union of a countably infinite number of disjoint sets is the sum of their individual measures. This property allows it to assign a consistent size to extraordinarily complicated sets, including the set of all rational numbers, which it elegantly proves has a measure of 0. A countable collection of points, it turns out, occupies no space. With this robust notion of measure established, Lebesgue constructed his new integral. The process unfolds with architectural logic. First, he defined the integral for a category of functions he called simple functions. These are functions that take on a finite number of values, each on a measurable set. A simple function is a finite linear combination of characteristic functions, where a characteristic function on a set is the function that is 1 on and 0 elsewhere. The integral of such a simple function is defined as the sum of each value multiplied by the measure of the set where it takes that value. This is the bedrock for a general non-negative measurable function. The Lebesgue integral is then defined as the supremum, or least upper bound, of the integrals of all simple functions that lie beneath it. For any measurable function that takes both positive and negative values, he decomposed it into its positive and negative parts. The function f is written as the difference of two non-negative functions, f plus and f minus, and its integral is defined as the integral of f plus minus the integral of f minus, provided both are finite. The power of this new framework was immediately apparent. The Dirichlet function, which had haunted analysis for decades, was tamed with astonishing ease. Viewed through the Lebesgue lens, the Dirichlet function is a simple function. It takes the value 1 on the set of rational numbers, a set of measure 0, and the value 0 on the set of irrational numbers, a set whose measure on the unit interval is 1. Applying the definition, the Lebesgue integral is simply 1 multiplied by the measure of the rationals, which is 0, plus 0 multiplied by the measure of the irrationals, which is 1. The result is 0. The paradox vanished. A function that oscillated infinitely between its values at every scale was shown to have a well-defined and intuitively sensible area. This was more than a technical fix, it was a profound re-envisioning of what it means to measure, to integrate, and to connect the abstract world of sets with the geometric concepts of length and area. Lebesgue had provided analysis with a new language, one capable of describing the universe of functions with unprecedented clarity and scope. The true power of Lebesgue's construction, the quality that elevated it from a clever extension to a revolutionary force, resided in its relationship with the infinite. The Riemann integral struggled profoundly with the process of taking limits. The question of when the limit of the integrals of a sequence of functions equals the integral of the limiting function was a source of constant frustration, demanding stringent and often impractical conditions like uniform convergence. Lebesgue's theory provided a definitive and far more generous answer, with two cornerstone results. The monotone convergence theorem asserts that for any sequence of non-negative measurable functions that increases pointwise to a limit function, the integral of the limit is precisely the limit of the integrals. There are no further conditions required. This elegant simplicity was breathtaking. Building upon this foundation, the dominated convergence theorem offered a tool of immense generality and power. It states that if a sequence of measurable functions converges pointwise and is uniformly bounded in absolute value by some integrable function, its dominator, then the integral and limit operations can be freely interchanged. The frustrating pathologies of Fourier series, which had motivated so much of this inquiry, was suddenly resolved. Pointwise convergence, a far more common and natural mode of convergence, was now sufficient under a very broad dominance condition. Analysts finally possessed a robust and reliable calculus for the infinite, a framework that behaved precisely as intuition suggested it. This newfound analytical power had immediate and seismic consequences for the very structure of mathematics. The collection of functions integrable under Riemann's definition forms a vector space, yet it is a space with deficiencies. One can construct a sequence of Riemann integrable functions whose limit is a function that Riemann's method cannot handle. In the language of analysis, the space is incomplete. Lebesgue's theory gave birth to the LP spaces, the spaces of functions whose pth power of the absolute value is Lebesgue integrable. These spaces, most critically the L2 space of square integrable functions, were proven to be complete. This property means that every sequence that wants to converge does converge to a limit within the space. This structural integrity, the absence of gaps, is the defining feature of what we now call a Banach's. This very discovery, that function spaces could possess such a robust geometric structure, laid the essential groundwork for the entire field of functional analysis, a discipline Stefan Banach and others would soon erect upon these pillars. The influence of Lebesgue's ideas extended far beyond pure analysis, providing the axiomatic language for a field once viewed as a loose collection of heuristics. Probability theory. In his 1933 masterpiece, Foundations of the Theory of Probability, the Russian mathematician Henri Kolmogorov performed a complete reconstruction of the subject. He explicitly adopted measure theory as its foundation. In Kolmogorov's formulation, a probability space is simply a measure space with a total measure of events, the outcomes of random experiments, measurable sets. Crucially, a random variable, previously a somewhat vague concept, aimed at precise identity as a measurable function from the sample space to the real numbers. The expectation of a random variable, its average value, was defined with unimpeachable rigor as its Lebesgue integral. This fusion of probability and measure theory was so successful, so natural, that today it is difficult to imagine the two disciplines. The legacy of Lebesgue's 1904 text continues to ramify through contemporary science and engineering. The modern theory of partial differential equations relies heavily on the concept of weak solutions, which exist in these very LP spaces and allow mathematicians to establish the existence of solutions for equations that model everything from heat flow to fluid dynamics. In quantum mechanics, the state of a physical system is represented by a vector in a Hilbert space, which is a complete inner product space. The most fundamental of these is the L2 space, the space of square integrable functions, whose completeness is a direct consequence of Lebesgue's work. The wave functions of quantum physics are elements of this space, from digital signal processing, which analyzes functions to extract information, to financial mathematics, which models stochastic processes. The integral of Lebesgue is the operational stat. In conclusion, the innovations presented in Intégrales, Longueur, ever more than an incremental improvement upon the calculus of the 19th century. Lebesgue's work constituted a profound paradigm shift, a refoundation of a central pillar of mathematics. By rethinking the act of integration from the perspective of sets and their measure, he forged a new and vastly more powerful language. This language provided the conceptual and technical apparatus to define length and area for extraordinarily complex sets, to tame wildly discontinuous functions, and to build the complete, stable function spaces that underpin modern analysis. He provided the rigorous framework upon which probability became a mature mathematical science. Lebesgue gave mathematicians a tool of unparalleled scope and reliability, reshaping the landscape of 20th century thought and providing the very grammar for large portions of the mathematics and physics that followed.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.